Hello, this week Group 5 will be discussing factors that focus on the mobility of radionuclides and their migration, and factors affecting migration. We will discuss this in relation to storage tanks, depositories, sorption and sorbents on their way, kinetics, and diffusion. The reference for this discussion is Bernard Bonin's The Scientific Basis of Nuclear Waste Management, Chapter 28. This text should be familiar as it was the reference text for the waste forms and waste fabrication module in this course. I will be covering the physical properties of waste. Some of it will be a little review, but it'll help tie things together, especially with the other two speakers, Carolyn and Wyatt. Carolyn will be covering geological considerations regarding radionuclides, and Wyatt will finish up with long-term storage considerations. I am John Hallahan, and I will be covering the physical properties of waste. The first property that we're going to be talking about is half-life. Radioactive waste can be characterized by the half-life or the activity of the material and the amount of material present. There are two different standards for characterizing radioactive waste, the international standard and the US standard. We learned about the US classes in last week's module, and we're going to go over the international ones here, and I'm going to relate them to how they tie to the US standards. We're going to start out with the graphic on the right and work our way up from the bottom going to the top. The first type of waste is mine tailings. This is mostly uranium daughter products with half-lives in the thousands of years. The activity level is usually very low, on the order less than 10 becquerels per gram. Normal storage for this type of waste is in situ storage. The mine tailings are covered by a layer of sterile rock or soil to prevent their dispersion, and also helps to screen the gamma radiation and to limit the radon off-gassing. In the United States, this is considered either uranium tailings or T-norm and is regulated by 10 CFR Part 40 Appendix A. Additionally, this waste is monitored for potential for migration into the groundwater. The next classification of waste is very low-level waste. This is usually steel and concrete rubble containing activation products. The activity level is usually in the tens of becquerels per gram, and the waste is sorted, decontaminated whenever possible, and then stored in surface facilities. Such storage already exists in France and Morbier. In the US, this is considered low-level waste, and depending on the half-life will either be Class A, B, or C. The next level of waste is low-level, short-lived waste. They can either have low-level, short-lived, or low-level, long-lived. It's usually gloves, boots, filters immobilized in concrete. The half-life is so short in the short-lived version that it will essentially be gone after 300 years. Activity is less than 3.7 times 10 to the 5th becquerels per gram. The waste is usually stored in surface storage of the concrete blocks in dedicated surface installations. The waste is stored above the water table, covered with an impermeable clay layer and a few meters of soil. Two such storage facilities exist in France in Le Hague and Silane. In the US, this would be considered Class Bravo low-level waste and is stored in compacted drums under a soil barrier at one of the 4 licensed facilities. The next type of waste is intermediate level waste. There's either long-lived or short-lived. It is usually processing residues and fuel claddings immobilized in concrete. This waste does not have enough activity to generate any significant heat. Half-lives can be in the millions of years. Activity is usually less than 3.7 times 10 to the 8th becquerels per gram. This waste could be put in underground disposal or near surface disposal. In the US, this is transuranic waste and is stored at the WIPP, or the Waste Isolation Pilot Plant in New Mexico. The last level of waste is high-level waste. High-level waste can be either short-lived or long-lived, but this waste is directly from spent fuel. The activity is usually greater than 10 times 10 to the 10th becquerels per gram. This type of waste is put in interim storage, either spent fuel pools or dry cask storage. In the US, this high-level waste has no long-term approved storage location. The next property that we're going to talk about is thermal output. Radionuclides decay and generate heat via their decay mode, decay energy, and half-life. The dominant mode of heat production is generated by alpha or beta decay, and not gamma or X-ray. If you think about this from an energy transfer standpoint, dumping 4 to 5 megaelectron volts in a short distance is going to generate a lot more heat than generating 1000 keV over the length of where a gamma will go. Radioactive decay in the material can also cause radiolysis, or the splitting apart of molecules. It can cause chemical changes or change the oxidation states, which will change the actual chemical reactivity of the material itself. If you look at this graph on the right, it's the heat emission contributors for spent uranium oxide fuel that's been cooled for 4 years. For short times, less than 300 years, you can see that the fission products, cesium and strontium, are the main contributors of the decay heat, but over the long term, once you start getting over 1,000, 10,000, 100,000 years, it's the long-lived actinides, plutonium, americium, and curium. This chart compares the heat release from a spent fuel assembly versus a vitrified waste product. This assumes that all the fission products from the spent fuel are still present in the vitrified waste. Based on the data here, a vitrified waste container requires about 2.15 spent fuel assemblies to generate the approximate same amount of heat, but you're saving a lot on the actual storage volume going with the vitrified waste container. Removing the plutonium significantly reduces the heat release by about 30% after 35 years and 60% after 100 years. And remember, in the graph from the previous thing, the long-lived actinides are the dominant heat generator. So if you remove the plutonium beforehand, that's going to go way down in the long term. It also removing the plutonium would enable smaller disposal facilities to be used. For reference, it takes about 1 kilowatt over an hour to boil 1 kilogram of water. This is taken from the National Institute of Nuclear and Particle Physics 2004 report by the National Assessment Commission in France. This graphic is a vitrified waste form from a light water reactor. As you can see, the constituents change as time passes, and as you get towards the end or that 300-year mark, that's where the long-lived actinides in there, the americiums and the curium. If this was a MOX fuel, it would have a higher long-lived heat output due to the higher percentage of americium plutonium. In this version, it would be 540 watts at 300 years instead of the 30 watts displayed. The goal is to have vitrified product remain under 100 degrees C in long-term storage. To use these vitrified types of glass, there's two types of glass most widely used in the world today, are the borosilicate glass and phosphate glass. Glass has become widely used for high-level waste, and that it is amorphous and less rigid structure of glasses compared to ceramics, which enables the incorporation of a very large range of elements that are atomically bonded in the flexible glass structure. The density of waste glass is slightly heavier than those of industrial glasses, owing to the presence of heavy metals. The viscosity at 1100 degrees Celsius is much lower. This is because the nuclear glasses are formulated to be poured at 1100 degrees Celsius, while the melting temperature of industrial glasses is significantly higher. This also minimizes the volatility of radioactive components such as Tech-99, cesium-137, and iodine-129. Glass transition temperatures occur in similar ranges, although it is slightly lower for nuclear waste glass compared to normal glass. The thermal expansion coefficient of the nuclear waste glasses is similar to that of window glass and significantly higher than that of Pyrex that you'd use in your kitchen. Pyrex is formulated specifically to resist thermal shocks, so you can go from hot to cold a lot easier without it shattering on you. Thermal conductivity is similar for all three types of glass. It should be noted that this low value is significant in nuclear waste glasses, which hold heat-generating fission products. The temperature at the center of the glass block needs to be controlled. That's why when you see these vitrified waste products, they're long, tall cylinders so that the center of the glass doesn't heat up a lot more than the outsides of the glass. Additionally, as you transition away from the fission products, the self-shielding of the actual glass itself helps diminish the gamma or the dose rate based off the radionuclides still left. Switching gears from heat production, now we're going to talk briefly about the chemistry of waste products. The dominant fission products that we're concerned about, cesium, strontium, behave as salt or metal. Cesium is an alkaline metal and will behave like sodium potassium chemically, and strontium is an alkaline metal and its behavior will mimic calcium or magnesium chemically. This doesn't matter when it's in the vitrified waste form, but if that starts breaking down or water starts getting there or it starts leaching into the soil, they'll behave chemically like that and then transport themselves in the same method. Strontium-90 is of major concern because it has a 30-year half-life and decays by beta 100% of the time. and its daughter product, which also decays by beta 100% of the time, has a 2.3 MeV beta. This is an extreme dose rate concern when dealing with strontium-90. Actinide chemistry also is dependent upon oxidation states. Since the most stable oxidation state for actinides, it changes depending on the pH or chemical reactions around it. The least soluble actinide oxidation state is +4. Therefore, precipitates can form at very low concentrations. These actinide chemistry affects the solubility and complex formation. Radiation can also cause changes in the crystalline structures of minerals and salts. This is seen in many areas to include nuclear weapons. Radionuclide migration, when not in a vitrified product, depends on three main factors. Advection, which is water flow through the soil. This is completely dependent on concentration and medium velocity. Molecular diffusion, which occurs when a population of microscopic objects, atoms, molecules, or electrons collide with obstacles in the medium. Or kinematic dispersion, and this is how much flow in a porous medium is broken up by solid objects that constitute the skeleton of the medium. If you look at the picture on the bottom of the slide, you can kind of see all three processes. Advection is the water flow going straight down the river. Molecular diffusion will be the water moving within that flow, just based on the actual kinetics of the molecules. And then the kinematic dispersion is the rocks in there, and you can see all the eddies and turbulence caused by this. And this happens on a microscopic scale when dealing with radionuclides. In addition to velocity, concentration also affects the length and width of the spread of radionuclides material. Think about it when you put a drop of food dye in a glass of water. If the water's not moving, it's going to slowly disperse out and it's all going to become homogeneous. But if you put a drop of food dye in a running stream of water, you have a small stream of dye going out and it'll spread out. As you have higher and higher concentrations, this can lead to larger and longer spreads. This example of groundwater solute plume model on the right here is just showing that, where you have your source term where the red is, and then it just slowly disperses out, and it'll be a longer, thinner thread if it has a higher velocity of the medium. Concentration will also affect the amount of sorption on the surface of the material, so depending on what type of rock or mineral it is, more of them may be stuck to the actual minerals themselves, and then that'll change how far it diffuses through the soil. Actinide migration is of particular interest because these are the long-lived things left after from spent nuclear fuel. Laboratory experiments suggest that actinides are very efficiently adsorbed onto many minerals present underground, especially clay, and are therefore almost immobile in an underground environment. This is measured by the spread of this is called a retardation coefficient, or R. An R of 1 means there's no sorption onto the solids, and it would just essentially just bypass the rock and nothing would stick to it. Most of the actinide values are on the order of 1,000. In Colovo-Oxfordian clay, the actual R values are somewhere between 10,000 and 638,000, which effectively means it's not going anywhere. The last thing we're going to talk about is radioactive tracers. There's two main types, perfect tracer and a non-perfect tracer. A perfect tracer literally just does not sorb onto the mineral surface, and it moves along in the solute at the same velocity that it does. A non-perfect tracer is able to be sorbed on the mineral surface, and it forms a concentration equilibrium with the radionuclide. Several types of sorption sites can coexist in the same mineral with different equilibrium constants. There's a thing called the distribution coefficient, or KD, and it depends on the cation, the mineral, and the water composition. If there's any concurrent ions in there, or a particular pH. Even in pure mineral phases, several types of sorption sites can coexist with various different KD values. So this is an extremely complex problem trying to figure out how much is actually going to sorb into the mineral. Take a look at the piece of autunite on the right here. You can visually see that there's multiple different types of minerals, and looking at the actual crystalline structure, you're going to have many different types of sorption site. So this is just one of the complex things that they have to think about when storing waste underground. In conclusion, we talked about different waste considerations, including half-life, heat generation, chemical properties, migration, sorption and solubility, and tracers. Here are the two references that I used for this presentation, and I want to say thank you and turn it over to Carolyn.
Hi, my name is Carolyn Halsey, and I will be discussing the geological considerations related to radionuclide transport. This includes the physical and hydrologic characteristics of the rock media and the water and solutes that flow through it. The purpose of deep geological waste disposal is to delay the migration of radioactive material as long as necessary for the material to decay before it can travel to the biosphere. Geological and hydrogeological factors influence how these radionuclides migrate through the ground and water system and therefore must be considered. These are the most studied types of rock media for current and potential locations of deep radiological waste. Granite is an igneous rock with a well-known water chemistry and very low porosity, but large-scale fractures are common, which can transfer radionuclides very quickly. Salt is also suitable and is already in use in New Mexico. It has a low water content and very good plasticity, so cracks are self-healing, but salt can contribute to corrosion, and the salt brines themselves have complex chemistry. Clay is a very fine-grained material with a high mineral content and can be used as both an engineered barrier and a host rock. Clay can have a very low permeability, causing slow water movement, and fractures in soft clay can be self-healing. It is chemically stable with strong sorption capacities, causing solute motion to be extremely slow. Volcanic formations are being studied. The only place it's in use is Yucca Mountain. It is an unsaturated medium due to being above the water table and being in the desert. The rock medium is characterized by its porosity and permeability. Porosity is defined by the open spaces created by the skeleton of the rock medium, and permeability is defined by the flow of water through those open spaces. These definitions are quite simple, but are complicated in practice by the heterogeneous nature of most rock. Large fractures, in particular, must be considered on an individual basis. They are complicated further by chemical properties of the rock itself. For example, clay contains many minerals that are negatively charged, so the porosity of the clay is not accessible in the same way for all radionuclides. Also, the porosity and permeability of rock is not permanent. Disturbances such as those during excavation or from the corrosion of storage materials can alter both factors of the surrounding rock. The rock and the water that flows through the rock will reach a chemical equilibrium, and this is referred to as the pore water composition. The pore water is characterized by its ion content, and this ion content affects the speciation of the radionuclides. Water is nature's way of transporting radionuclides away from deep repositories, making hydrology quite relevant. It can be studied by two methods, looking at the movement of the water and looking at the movement of the solutes. The three main factors that influence solute transportation are described by advection, diffusion, and dispersion. There are other influencing factors outside these three, such as chemical interactions, but these are the big three. Advection refers to the general flow of water with the solutes following right along. The advection flux can be calculated simply by multiplying the solute concentration by the velocity of the water flow. A little more on that when we talk about Darcy's law in the next slide. Diffusion on the molecular level can be influenced by several factors, including the solute concentration, thermal changes, and the porosity of the medium. Diffusion is the only one of these three that can occur without water flow. Kinematic dispersion takes into account the skeleton of the porous medium, as the structure of the pores can take on various shapes. The water may flow through a path created by microscopic clay particles, or larger grains of sand, or perhaps a fracture through a solid rock formation, all of which will result in diversions of different shapes. In general, Darcy's law describes how much water moves underground under the influence of pressure gradients. It's calculated by factoring in the permeability of the rock medium and the slope of the water flow. The law assumes steady laminar flow through the saturated soil. Given these assumptions, it's not surprising that it's not suitable for all situations. For example, it's found to be invalid in some very low permeability mediums, like very soft clays. An aquifer is an underground medium permeable enough to allow the water to circulate, typically resulting in a horizontal water flow. An aquitard is an underground medium with little permeability and therefore tends to have minimal water flow. This water flow, when it does happen, is typically in a vertical direction instead of horizontal. Aquifers have a higher permeability, higher porosity, a hydraulic gradient, and water velocity than aquitards. And due to the minimal water flow in aquitards, advection and dispersion are minimized. Long-term repositories will typically be below the water table, meaning the surrounding rock will be water saturated, like these two examples. A unique exception to this would be Yucca Mountain, which is in the desert and well above the water table. Sorption is the fixation of an atom or molecule onto a solid surface. When an ion or radionuclide sorbs to the rock medium, it decreases the concentration of that solute. And depending on the amount of sorbed material, it can also change the porosity of the rock medium. Clay has a high sorption capacity due to the negatively charged minerals it contains. Clay is also alkaline and reducing, which can affect the solubility of radionuclides. At some point, the sorption capacity of the rock medium will saturate, and the medium will reach an equilibrium with the water. The result is the pore water composition that we talked about earlier. The ionic content of this water can alter the species of a radionuclide and therefore affect its solubility and sorption properties. As the solubility of a radionuclide decreases, its solute concentration will decrease, which means transport will also decrease. So these two factors, solubility and sorption, significantly influence how radionuclides are transported by water underground. To tie it all together, the transport of radionuclides is affected by chemical, geological, and hydraulic properties. The rock-water equilibrium determines the pore water chemistry. The pore water chemistry affects the speciation of the radionuclide. The radionuclide speciation determines its solubility and sorption properties. And those solubility and sorption properties affect how the solute is carried through the rock medium by the water. This is the general concept behind radionuclide migration modeling, but there can be many variations depending on the specifics of the real-world location that's under investigation. So we've covered a lot of different ideas from several fields of study that affect radionuclide migration in an underground environment, all of which play a role in site evaluation for the deposition of radioactive waste. We have geological factors to consider, such as porosity and permeability. We have hydraulic descriptors, such as advection, diffusion, and dispersion. And we have chemical properties, such as speciation, sorption, solubility, and pore water composition. That concludes this section of the presentation, and I'll now hand it over to Wyatt.
Hello, my name is Wyatt Flukiger, and I will be talking about long-term storage and the barriers, costs, impacts, and timescale challenges being faced currently. There is research taking place around the world on waste repository functions, needs, and requirements. Table 25 on the right has a list of countries, location, the host rock, and main backers of this research. As some of these rock natures were new to me, here's a short description of them. Tough, relatively soft, porous, generally formed by compacting and cementing of volcanic ash. Rock salt, also known as halite, is a layer of sodium chloride salt deposits underground with other trace minerals. Granite is a cooled magma at depth rich in quartz and feldspar. Calcic clay, absorbent clay formed after volcanic ash that's rich in calcium. Tonalite, a type of granite, contains a higher percentage of plagioclase feldspar. Now, the current cost estimation in this chapter at the time of writing was roughly $15 gigadollars, the next step above billion for the construction of a site. Of this estimate, 40% is exploitation, being the cost to physically construct, the salary of workers, and supplies needed for the location. Another 40% as well to create the opportunities and drive interests of assets to work on such a project to bring additional companies in. The last 20% is for everything else cost-wise. This would be taxes, insurance, conducting studies, unforeseen costs, etc. The concept behind the effectiveness of these long-term storage geological sites is to implement multiple barriers. This idea has been broken down into three main areas of focus, these being the matrix, engineering barriers, and geological. The matrix is the material used to host the waste. Glass, concrete, metal, and ceramics can be used to be blended with the waste to hold it from being transported into the surrounding materials as quickly. This matrix is generally housed in a metal container. The engineered barriers are construction efforts to slow migration and shielding of the thermal, hydraulic, mechanical, chemical, and such variables. This includes the liners, the walls, and the site fillers that will be shown more in depth on the next slide. Lastly, the geological is the natural formation between the repository and the biosphere. Looking on the right of the image, there is a puits de pommage, which is French for pumping well, rivière, and fracture, to give a rough idea of the scale of the depth of operation, as well as areas of concern for migration that will negatively affect the timescale of. To meet the multi-barrier concept design, architecture has been proposed. As no current long-lived repository is currently in operation, there has not been a clear definition on architecture needs for long-term repositories. As needs vary from site to site around the world, it will be important to define the minimum needs of a repository for longevity and safety of the surrounding impacted biosphere. One of the most important variables is the thermal load, and currently the standard is set to 100 degrees centigrade, as the only way to remove heat from these sites is through conduction to the surrounding once the repository is sealed. This limit is to reduce potential thermal stress and fracturing experienced over the facility's lifetime. This equates to a power density less than 10 watts per square meter and will depend on the host rock what the facility maximum will be set to, as locations will vary in this regard. This temperature is also calculated to be reached at roughly 40 years after being closed to filling operations. Table 13 below shows a general breakdown of different properties of host rocks and how they compare. Looking at the table has some pros and cons. Granite is being studied in places like Switzerland, salt here in the USA, and clay in France and Belgium, as a short list. On the right are examples of general repository design concepts, showing how waste will be stored and the barriers put in place to separate it from the environment, and materials used to really protect us as a whole. The study of the areas directly around the repositories are labeled as near and far fields. The near field is the area directly altered by man-made actions and to a depth that directly feels the stresses from these actions. These actions being the thermal, hydraulic, mechanical, and chemical, as listed with examples of each as so. The far field is any area beyond that that is not directly altered by human actions and tends to have a small gradient of change in these types of stresses as well. On the right is a breakdown of the kinds of stresses the near and far field are put under during their operating lifetime, and at what time in years that they tend to take place. As shown, the near field has many stresses that affect it over the first million years, whereas the radionuclides are calculated to start their migration at around the 10,000 plus mark when you look at the far field. What leads to that 10,000 plus year mark is through the calculation of transit factors. Corrosion, the form of waste, and hydrogen are some of the factors that affect this calculation. Corrosion is calculated at 0.2 to 2 micrometers a year for steel that will be used for waste containers, liners, and other facility barriers. This is due to oxides and hydroxides having chemical reactions as well as sulfuric acid produced by pyrite in the nearby soils. Concrete barriers will also have corrosion through carbonation, forming porous surfaces and leading to a leaching fracturing in the structure. The waste form also plays a role as different matrices break down differently and on different timescales, slowing the release of the material. Hydrogen plays a role as it is produced through radiolysis through radiation exposure to water and steel corroding in an oxygen-deficient environment. This increases the pressure of container vessels and the architecture, leading to fractures, making pathways for waste to travel through, be it the host rock or the containers themselves. As shown in Table 27, it is estimated that it will take 70,000 years to bypass the engineering in Aquitard, and another 100,000 to get into the general water supply of the biosphere. Time is the most important factor of these repositories, as with time, radioactive waste undergoes half-lives, becoming less hazardous in this regard. Over the first 1,000 years of the facility, the major milestones will be heating to 100 degrees Celsius, resaturation of the clay barriers hosting the site, settling of the structure, and the fissure fractures formed from this. As shown below, the fission products will become stable, reducing their heat load and no longer be a concern for the primary. This leaves the actinides and plutonium for the long-term stresses. On the right, it shows how the heat load will disperse and equalize with the surrounding in the far field. This is what leads to the fissures and settling from thermal loads. 10,000 years and beyond is when the next major events start to occur. This is when the migration of the radionuclides start as it begins leaving the glass and host matrices. This is when environmental impacts will begin in the near field as well. The better the barriers and delay factor, the slower this release will be. As shown in Table 28, some of the important radionuclides will no longer be an issue at this point. The image in the lower right shows how fission products and mixed actinide glasses will generally no longer be a radiotoxicity relative to natural uranium as well. This leaves the plutonium and some of the mixed actinides like cesium-135 and technetium-99 and oxide as the main contributors to environmental exposure in the long term. This breakdown leads us into public dose. The results of the PADRS exercise have estimated that over multiple scenarios in clay, granite, and salt strata, it shows that exposure is many factors below limits and background values. The Department of Energy has set values in 40 CFR Part 197 for repositories as listed here. The first values are for the general environment affected by the repository, such as the entrance and surrounding area that would be present during loading operations. So during these operations, it is 150 microsieverts a year as well during the first 10,000 years after initial closure. Afterwards, this value is increased to 1 millisievert per year, which if the PADRS study is relatively accurate, then these values are currently met by proposed designs and well below background radiation levels. In conclusion, nuclear waste will be with us for many generations. This makes waste management an important consideration for the future of mankind as a whole. These are the references that I used for the long-term storage part of this presentation.